tough. Okay, students. Let's get rolling. I'm going to talk about the midterm a little bit. We don't have a whole lot to say right now today because it's not completely graded. And then we're going to talk about oscillation, because what we're shooting for is chapter 7 and 8. And I want to go through oscillation with you one more time and do some integrals and stuff before we get deep into the nitty-gritty of chapter 7 and 8. Now, let's do some comments on the exam. As I mentioned, we're grading everything. There's no results to say yet, although I graded the skull of Mount Vesuvius and the other problems for about 7 students, and it looked fairly good. Some people had some problems. The scantrons are in, but it's hard to tell when the scantrons come back. You know, it's unpredictable. So it's supposed to be 2 business days. So we got them in yesterday around lunchtime, and so hopefully it could be right now. I mean, they could be in right now for all I know. I won't release them until I convert them. You'll see when they finish, they'll post them automatically into the grades page, but they'll mute the information. So you'll see that you have something from the Scantron on the midterm, but it'll be something out of 18 points. So basically all I have to do is take that row of the grade book and multiply it by 2, and that'll be your Scantron score. And I'll show you what all that looks like in a few minutes. Now, the other thing is Tyler Campbell. I get a lot of your guys' names. I know a lot of you, but not everybody. I know the faces and names for quite a few of you. But for some reason, Tyler, I keep calling him Will, because he looks like a guy I knew in grad school named Will. And the other thing I keep calling him is Kyle. I don't know why that is. Maybe it's because of Terminator. You know, Kyle that comes back in the future. The first Terminator. Anyways, so Tyler, we can use the Speedgrader. Okay, so if you've graded those, did you put them in yet? You can put them in, just like normal. Okay. All right. So Tyler and I will both be putting in grades as we score them, or we'll be putting in scores as we grade them. And I'll have some comments. We'll go over a couple of problems. Problem 3, clicking data. I have to take that apart so I can look very carefully at what you've clicked in. We've got 5 items, so it's gonna take a little bit of analysis. And the reason for that is I like to give partial credit. Like a student told me after the exam, oh, I forgot to square the speed, for the drag force. And so I should be able to spot that by looking at her raw data. All right. So in other words, it's not going to be automatically graded. I'm going to look at them all very carefully for each, especially the numeric questions. The multiple choice there's only one answer there, but all right. So problem 1, either you had a tiny calculator, a tiny chicken, or a tiny rubber duck swinging. That was basically a banking angle type question, centrifugal force. I'll go over that with you in a few minutes. Problem number 2, the mysterious crystal skull of Mount Vesuvius, the crown of good Princess Winifred, and the Marquesa, Lucia, Emerald, astounding. Those are basically Spider-Man problems. And I don't, and that's the first one that we're grading. By the way, some of them look good. So there's a lot of people that crushed it. And there was a couple people that I expected to crush it that didn't. And I'm not going to look at anybody, but I could. The ones that I graded, there was a couple people I expected to crush it that didn't, but still got points. Now, problem 3 was basically a free fall equations of motion problem, which we've done out the wazoo. And then inside of that was a small drag calculation. And I'll try to go over those ones. Now, up at the top, I say that we will enter the problem scores as we grade them. So what it's going to look like is this. We'll be using something called the Speedgrader to put in your score for midterm question 1, 2, and then I'll be doing this. I'll upload this one so everybody will get this grade, the iClicker grades at the same time. But number 1 and number 2, I'll be grading number 1. Tyler's going to be grading number 2, and I'll be grading number 3, including partial credit. And then here's the Scantron. So that I'll be uploading that. It's basically going to be double whatever the Scantron raw score is. And then when we have all of them together, I'll calculate the midterm. But until I get all the data in for all the problems for every student, you can mentally fill in your midterm total. It's just the sum of the 4. And now nobody's got anything in there right now, but as soon as you got the first 4 here, you can mentally figure out the total. Just add them up. All right. Questions about any of that? All right. Let's keep going. I wanted to take some survey questions about the test. Turn on your clicker. We're going to be alphanumeric, so you're going to have to hit the send key. And your first question is, how did you feel about the Scantron part of the test? All right, so now every answer is correct. Just type in whatever you think describes your feelings. We'll take a look at these results. Can you guys take a count, please? Okay. I'll just grade all these. So A, B, no, don't type in a word. Type in, just type in a letter. Keep it, we'll save your soliloquy for another time. Okay. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Let's take a look at this one. So there were a good fraction of you felt really confident you crushed the B pretty good. C, mezza, decent, not sure how well I did. D, major problems, just 2 people. All right, I guess that's acceptable. Now that doesn't tell you what your grade is, but it tells you, what you're feeling about it. So that's really what I want to know. Okay, next question is, how did you feel about the problems? Okay, so same thing here. All right, go ahead and type in A, B, C, D, or E, and then hit the send key. What do you got?
71.
I'm getting 71 answers here, so that's good. So this one, I can grade this one as well. Everybody gets a correct answer here. Ten seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Come on, there's 2 people that didn't vote. Give me a vote. Well, that's tough noogies for you. You don't get any points today. All right, let's take a look at that one. Okay, so this one is a little bit different. Not so much of category A. A couple of you only one problem. You know what I should do? Let's do another. We'll do a verbal problem. C, a bunch. That's the biggest pile. Decent. Not sure how well I did. And hey, you guys, that's normal to not be sure how well you did. You know, especially on any exam. Sometimes you feel, oh man, I totally blew it, and you end up with a decent grade. Sometimes, oh yeah, I think I did it all right, and you end up getting crushed instead of crushing the exam. So it's hard to predict. E, D is, those are both fairly small groups, 5% of the class together. All right, now let's do a verbal question. Type in one of the following 4 options. I want to know if you had a problem, the one problem that you had a problem with. So type in I for Roman numeral 2, or I for Roman numeral 3. Or if you crushed them, just type in I crushed them all, or something like that. So give me Roman numeral I for problem 1, if that was your toughest. Roman numeral 2. What? Yeah, why were you going shh? What? Yeah, so Roman numeral 1 was the chicken, calculator, or rubber ducky. Number 2 was the Spider-Man problem. And number 3 was the trajectory problem. Okay, take 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Nice. 74 people voted. That's good. This is going to be helpful for me. Okay, stop. Let's take a look at this one. Well, we got a bunch of. Crushed them. Okay. Okay, what is A supposed to mean? All right, who? I'll give it credit here. Who typed in A? Does that mean you aced it?
No, I don't have time to actually type something.
Okay, Roman numeral 1. Okay. Come on, baby. I got crushed. One person. Okay, 1 and 3. I cruised them. I'm going to leave that incorrect. No, I'm just kidding. Let's see if I can get it. There we go. Everybody gets a correct answer. Let's see what else we got here. Number 3. Oh my goodness, that's a big pile. So it looks like, wow, over half the class got, yeah, we'll talk about that in a few minutes. Anyways, everybody, this is a survey, so everybody gets a point on that one. Now, I want to look at some of the problems with you. So let me switch over to the document cam, and we'll go over some of the concepts. Tyler, what is that? Can you have an explanation of that, or? A green vector. All right, let's see what we got here. All right. So I'm going to give some comments on the written problems. The first one I'm going to comment on is, whoa. Oh, can you help me with this? The first one I'm going to help you with is the skull of, or is the rubber chicken. I need a string. Is there a string around somewhere? Does anybody have a piece of string on their table? All right, I'll have to use something else. Anybody got a lanyard with keys on it around your neck? Can I borrow that? All right. All right, so this is not a rubber chicken. It's not a pair of fuzzy dice, but it will show you the basic idea. If you're in a car and you're going straight ahead at constant speed, this is what it looks like. As soon as you turn to the right, you accelerate to the right, the keys swing to the left. All right? Now, the reason that was on the, now the, and the opposite is if you turn to the left, made a turn to the left, the keys swing to the right. Now, that's a critical decision to make. All right, here you go, Kirsty. Because otherwise you can't draw a free body diagram if you don't know which way it swings. So that was, and also hopefully you correlated with the multiple choice item about the UCF shuttle bus. Raise your hand if you caught that. Okay, good. That's why I put that one in there, to jog your mind about what happens when you accelerate left or accelerate right. All right. And I didn't want to put acceleration forward or backwards because I wanted left or right swings. But let's do that free body diagram now. All right. So we'll just do some sketches here and talk it over. So here's your circle, right? So you're going around like this. So you're right here. Let's just say you're right here. So your velocity is like this. This is kind of an overhead view. Okay, here's your radii. Okay, and you had all the radii and stuff, 50 meters, I think it was for everybody. So this is V. Your centripetal acceleration is inward, and I think you can actually work this one in terms of accelerations. Anyways, the free body diagram. So this is turning right. Okay, so this is kind of the layout for it in 3 dimensions. And if it's in terms of the rear view mirror, you turn right. So here's the rear view mirror. Here's your eyeball looking in the rear view mirror. Here's your ear, etc. Actually, that looks like an amoeba. So let me cross that out. Anyway, so here's your rear view mirror. Try to do a better one. Okay, so this is like from the 60s. And so you're turning right. So your rubber chicken, I'll just do the calculator because it's a rectangle. So your rectangle's out here, right? And here's your vertical. So this is your angle theta. All right, now that's what happens. All right. And that means that, so your acceleration is this way. So the centripetal force also is this way. Now that's the net force. All right. And that's going to be mv squared over r, all of which you could calculate. All right. So you can get that But the free body diagram is going to look like this. So you're going to have some tension. So here's the string holding it up. So you're going to have a tension up at this angle like this. Okay, you're going to have some downward newtons from the weight force, which has got to bounce the upward component here, 3, 4, 5. So I'm going to make my weight force 5 blocks down. Okay, so there's the weight force, which you can also calculate. And here's the tension in the string. And here's theta. Right. No, I take that back. Here's theta. Okay, and here's theta. Okay, and this is your unbalanced force. So this is your net force. As far to the right, make it like that. mv squared over r. So the thing here is that you can calculate this, you can calculate this, and so you basically have this right triangle. So you can do inverse tangent of these two forces and get theta. And I believe that was the calculation that you were to do. So I'm going to be grading on your free body diagram. I'll be grading on your strategy if you have some. Hopefully you don't have numbers everywhere. And then theta, the angle of tilt. Okay. And actually, I think I actually asked you which direction as well. But if you have this, you know, it's auto. I mean, if you have this, automatically you have the right direction. Now, if you're doing a leftward turn, counterclockwise when viewed from above, then you'll be swinging over the other side. So there's several different versions of this. All right. Now, I'm not going to comment on the. No, I guess maybe I will. I'll do number 2, the crystal skull of Mount Vesuvius, or the little jewel of Princess Lucia, Marchesa Lucia. All right, so this is basically a Spider-Man problem. Yeah.
Is that a 0 inside the?
Here?
No, the first.
Here?
Yeah.
That's a cross out. Yeah. Theta is this angle. The swing angle is here, so it's up here at this one. All right. So the emerald problem is basically the Spider-Man problem. I don't know. I saw some people that I expected to crush this one. I expected a lot of crushing because everybody crushed the homework, and this is basically homework 4 done over again. But there were people, for whatever reason, they didn't crush it. But Tyler and I are giving partial credit, so we know. You know what I noticed is that a couple of people did the trig wrong. They made trig errors, and so we're giving partial credit. And then they got everything else right on this problem. So we'll grade that accordingly. Now, another thing that can you advance my slide? Hit the leftward arrow key. Okay, good. Thank you. Now, here's the Area 51 problem. Alien technology. Basically, all you had to do was, you know, X of t and V of t. Simple. Dr. B giving you a break, 45-degree angle, very cinchy. Some of you had an initial velocity of 544 meters per second. So Vx and Vy of 0 were 385 approximately. Okay, now that tells you the drop time, delta t, and the rise time. Now you didn't have to do this, but I did it when I set up the problem. Delta t is equal to the amount of velocity lost minus 385 meters per second divided by g. And the reason that is important is it tells you how much time it gets to the apogee. Now, you didn't have to work with the apogee in this problem, but I did want to make sure that everybody got a point somewhere on the way up. So there's your point in question. Now, you didn't have to verify that. Matter of fact, you really didn't have to do a whole lot with this one. All right, because once you get, once you get this here, 385s, and it's 385s both sides, your equations of motion are a piece of cake, what we describe in physics as a walk in the park. Y of t, we've done it as about 5 zillion times. If this is the origin over here, 0, 0, where it launches, then you have 385 meters per second times t plus a negative 4.9 meters per second squared times t squared. And then the Vx, this is really what you needed because I'm asking you about the velocity at this point. So this is V at, for this one, it was the velocity at 12.0 seconds, I believe. So you need V of t, the x component of V of t, which is just basically 385 meters per second. And why is that? Why is that a constant? There's no such thing as horizontal gravity. All right, so that was the easy one. All right, and Vx of t, or Vy of t, I should say, is also 385 meters per second plus gt. So you can figure out Vy of 12.0 or any other time from that. And then you just got to do inverse tangent and stuff like that to get the tilt angle. The drag force will be exactly the opposite direction. So something like this. And then the centripetal component of G, G is straight down. So that's a centripetal force. It has a component of centripetalness, and that's perpendicular to so this is the V that we want, and so the component of the gravitational attraction is in this direction, or the gravitational acceleration, I should say. So if you figure out this, so this one is basic here. If you can get 385s for free, basically for free, then you can set up x of t and y of t. Then you can figure out these two, Vx of t, Vy of t, and then do a little trig and get this angle here. So this is the reference axis. So I'll call this alpha, and then this one here is beta, and then this one all the way around to here we could call gamma or anything else. You can figure out all those. Once you get these two babies, these two components, you're just doing some inverse tangent and then figuring out a little bit of geometry for that. Now the other question was the magnitude of the drag force, which is 1/2 rho of air times the coefficient of drag times the area times v squared. And so you have to, square whatever this is, and then square 385, and then put it in here, and then do the rest. So that's a little bit of a plug-in problem. And then at the time that I say, you instantaneously turn on the atmospheric effects. So that's why it has to be classified as alien technology. Because in reality you can't do this, but in Hollywood you could. All right. So that's why you get the drag force and stuff. And the question is, how does it make things turn? What it does is it gives you this force here. it slows you down. And so basically, you're not going to go as high, and you're going to, let me do this in red. You're going to curve a little bit more. So let's say this is where it turns on. At that point, you start diverging and following a different arc. It's not going to be a parabola either. But it is going to curve a little bit more. And that's that was the answer to the multiple choice. So, questions about that one from Area 51? I'll put my full solutions online. This is just a kind of a headline view. Cecilia? Huh? Right. And the idea is that at this time t, I'll do a blow up. So here's kind of a generic direction for this one, 12.0 seconds. Some people had, remember how I had 27 seconds and 17 seconds and all that stuff? And we had to make sure everybody was coordinated on that and the typos. So everybody had a different time. But Cecilia, here's the horizontal component of it. Here's the vertical. You know, and I'm not saying that this is, so here's the angle alpha that you want to answer. But this is Vy of 12.0 seconds. And this is Vx of 12.0 seconds, which is guaranteed to be 385 in this problem. I can't remember. Let me look at my notes here. I might have done this one already. No, that's from lecture. I guess I have it in my notes somewhere else. But anyways, the alpha is the arctangent of whatever you get for Vy of 12.0 seconds divided by 385. All right. So see, where did she go? Oh, there you are. Does that make sense? Yeah. So once you get alpha, then opposite that is the drag force perpendicular to it, because the centripetal acceleration is always perpendicular to the velocity. So if you figure out the velocity angle, 90 degrees more will give you, or 90 degrees clockwise will give you this one. And the reason I put everybody up here, I didn't just give a random number here. I want to make sure that it was, part of the way up to apogee, because I wanted V to be first quadrant, and that makes these other angles manageable to grade. So it's still going to be tough to grade all this stuff. Another question? Robert, got a question? All right, let's keep going. Let me go back to the regular lecture. Okay, so I'll be embedding that diagram in the lecture, in the YouTube, a little bit later today. Now, and we'll talk more about the exam probably Tuesday when we have everything in. I might put an announcement in a discussion post about something if I feel it's important. But definitely we'll talk about it again on Tuesday. So, because then we'll know, okay, here's where people got tripped up a lot. Tyler, I'm going to want to know what the common errors are, if any. So just kind of keep a mental note. And I'll be doing the same with my stuff. Now, we're going to push forward. And our main objective now is the study of energy and momentum. Chapter 6 is in the rearview mirror now. We're going to push forward into chapter 7 and 8. And chapter 7 and 8 are a systematic treatment of energy. And we're also going to do a systematic treatment of momentum and angular momentum. Those are the three dynamical quantities on which the universe depends. You know, forces and stuff like that are related to momentum, angular momentum, and energy. Curvature of space-time. All three of those have an effect. So chapter 9, 10, and 11 are also in our sites. That's about momentum and angular momentum. And some of it we already know. But I want to emphasize these three terms because of basically because the universe that we live in is a four-dimensional space-time. And for that reason, energy and momentum form a complete dynamical vector in four dimensions, which is how it all works. And angular momentum is factored in slightly differently, but we'll see about that as we go. Now, I have a couple more clicker questions for you. This white substance on the screen is what we call snow. That's one of my former students who now lives out in Montana, plowing her driveway to get out to the, out to the mailbox and whatnot. I love it out there, but definitely a lot of snow. And you can see on this, a snowdrift. Now just think about driving your car, and actually you can see some look at this out over here. I never noticed that. How did that get like that? That looks all blooped up over here. All right, somebody must have taken the turn a little too fast and went plowing right into that. So anyways, let's do a couple IQ test questions. Now, go ahead and hit the refresh key because these ones are going to be multiple choice. All right, so hit the refresh key and just think this one over. Two identical cars at initial speed 5 meters per second. A snowdrift and a brick wall. I forgot to put all of the above, including none of the above. So go ahead and vote for that. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 76 students answered. All right, let's take a look at what you guys have got here. Yeah, the brick wall is the one. And the way to think about that, let me just grade this one real quick. Oh my goodness. Uh-oh, we got some talking to do. All right, not everybody answered that. Both exert the same force. Incorrectamente. All right, let's talk about this. All right, so take some notes, all right, of what we're about to say. The two cars are going at identical speeds. So the delta V for stopping is the same, minus 5 meters per second. I mean, if it's going in the x direction or something like that, the x-axis. All right. Now, here's a question for you. Which one brings the car to a stop more quickly? The snowdrift? Now, this is for people that have driven in snow. Raise your hand if you know the answer to this. Which one brings it to a stop more quickly, the snowdrift or the brick wall? Because those of you guys from Florida don't know jack about snowdrifts. So what do you think? Brick wall it is. Shorter stopping time. So the interaction, so delta V is the same for both vehicles, but delta T is smaller for the brick wall. And it takes you a little bit more time to come to a stop in a snowdrift. I know that from direct experience. You know, you just kind of, and here's the other thing. A brick wall, think of this. It has to exert some force on your car, all right, in the opposite direction that you're going. So it has to exert some force to stop you on the front end of your vehicle, all right? Now, a snowdrift is not going to bash in. It's going to exert some force, but not enough to bash in the front end of your rig most of the time. But a brick wall, definitely. So that means a big force. In terms of the interaction time, the snowdrift has a big delta T. The brick wall has a small delta T, Zadriana. And so the numerator, delta V over delta T, for the brick wall is same numerator, smaller denominator, bigger quotient. And what is delta V over delta T? Acceleration. And they're identical cars, so the mass is the same. So the F equals ma, no matter how you look at it, in terms of bashing in the front end or in terms of delta V over delta T, F equals ma is bigger for the brick wall. All right? Now, next question. Okay, you have two cars that are both traveling. So this is pretty pathetic, 2 meters per second. It's about 4 miles an hour. But now this time there are two different masses. And so you have a rope tied to the end of it. And like the burly beast that you are, or that you wish you were, you exert 1,000 newtons backwards. So you're going to get dragged a certain distance. You're still able to exert 1,000 newtons, but you're getting dragged. So which one drags you the longest? Let me start the question. "15 seconds to vote. 10. No, 15. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Taylor, great to see you. Make sure to review the YouTube after class. All right, let's see what you guys got here. Yeah, Escalade, you guys are geniuses. Now, this, go ahead and make your note, a note. Jot down this problem. It's good for your notes. Distance and force. That is something related to what we call work, F delta X or F delta Y if it's a downward gravitational force or anything like that. Wherever the direction of F is, if it's also parallel or anti-parallel to the direction of your motion, you're going to gain speed or lose speed. And so this thing, to stop the car, with a certain amount of force, you're going to need a lot more F times delta X with the Escalade. So, so what we're going to do is figure out and kind of systematically in chapter 7 and 8, we're going to work on why that is the case. All right. Now, this is just a little tiny taste of chapter 7 and 8. So energy and momentum and angular momentum, which is where we're heading, and they're crucial concepts, very important concepts physically. But what I want to do now is work with you on a very simple force and start working out all this stuff in terms of oscillation. So I want to give you a little bit more instruction on the force that controls oscillation. And this is a figure from chapter 5. All right, we're going to be doing, so we're dipping backwards into chapter 5.6, which is a little blurb on spring forces. And then we're going to dip back forward into chapter 15.1 and maybe 15.2. Um, and then when we're done with that today, then we'll have a really good force to work with to understand just about everything you need to know in basic terms for energy, momentum, and angular momentum. All right, so let's go back to the document camera. And Quinn, can you be ready to turn the pages? Start with this one. And let's go to, let me make a note here. This is 22720, page 2. All right, now let's go to page 3. And we'll talk about page 4, spring force. And we've already talked about it a little bit, and we saw that diagram. The basic idea with a spring force, let me draw a little diagram here. Let's put a little mass on a frictionless table. And I think we're going to break out some equipment next week, maybe. Do you guys know how to do the air tables or the air tracks? Have you ever done air tracks in here? They're all over there in the corner. We're going to have to do air tracks next week, I think. So let's give this a mass M. Let's attach, so this is the wall over here. And here's the tabletop. So this is a real simple picture. And so let's draw a spring. It's kind of hokey, but it's good enough for government work. And let's say that this oscillation goes left and right, okay? And we've seen it, it'll go back and forth around the equilibrium point. And the spring force, the law for the spring force is, let's call this the x-axis here. Now we're not going to worry about the y-axis because it's one. For this case, simple case, we're talking one-dimensional motion. So the force law is F equals minus kx times I hat, all right? And K is known as the spring constant. And it's kind of like the property of a spring by which you encode the stiffness, okay? How stretchy is it or how tough is it to stretch, okay? So that's a spring constant. And this is also known as Hooke's law, after Professor Hooke that figured it out and kind of enunciated it. But I never refer to it as Hooke's law, but the textbook does. So when you see that, they're talking about this force equation up here. Now that's important for us because Newton's second law which is F equals ma, all right? And I'm dropping the vectorness in this because we're in one dimension. So that becomes, for us, minus kx equals ma. And prior to this, we have not put in a specific force law over here. Although another force law is easy to put in here, and I think we have done that, the downward gravitational force, mg, okay? And that one's easy to integrate. Right now, remember, this is equal to m times the second derivative with respect to time of x of t. All right, so we're talking about a differential equation. So let's write this down. K minus kx of t equals m times d squared by dt squared of x of t. Okay, so that's a differential equation. It's a very pervasive and important differential equation. Everybody in here that's going into engineering and physics, you're going to need to know this, like the back of your hand. And you probably won't know it like the back of your hand until sometime after this course, but we're going to give you the basics in this course. All right, now let's take a look at some of the properties of this. Let's define, if you look at this, the force law, the force is equal to 0 at x equals 0. So let's say that this point right here underneath the mass, let's say that that's x equals 0. Okay, so right there, the force is equal to 0. Now, as you know, if you stretch out or compress, so this is the compression side, and this is the extension side. And the motion is symmetric left and right of equilibrium. This is called the equilibrium point. Okay, equilibrium because the force is 0 there for just the instant of time that it moves through that point. So F is equal to, and if we think of this as the rigidity force, the normal force, let's write this down. If the sum of the Fy's equals the normal force upward plus mg downward, if that's equal to 0, all right, then whenever Fx is equal to 0 newtons, we have equilibrium, and that's why we say that x equals 0 is the equilibrium point. Now, it's dynamic equilibrium. In other words, you're still in motion as you pass through that point, unless you don't stretch it out. If you just let it sit there and vegetate at that position, that's what you call the unstretched. Let's make a note of that. The unstretched length, which also means the uncompressed length. If you compress it a little bit to the left, it's going to bounce back. Okay, so if you compress it over here to the left, you're going to get some rightward force, and it's going to bounce back towards equilibrium. But then as soon as it gets over here on the right side, it's going to bounce past the equilibrium and go out here to the right. It's going to start feeling more and more leftward force. All right. So that's going to slow it down and then start it moving back towards equilibrium and then back over all the way to the left to max compression. So let's make a little table here. Position, force, direction. X less than 0, the force direction is rightward. All right, x equal to 0, zip zap. It's equilibrium. If your position is x greater than 0, then your force direction is back to the left. And my wonderful students, this kind of a force law is known as a restoring force. Okay, and it's not the only kind of restoring force that you can get from nature, but this one is ubiquitous. It's everywhere. And engineering and physics majors, chemistry majors, you're going to see it out the wazoo. Cecilia, question. Zero. Zip, zero, nada. So that's your equilibrium point. Okay. All right. So when you're over to the left, x is negative. See over here, if this, Cecilia, if this is 0 here on the x-axis, then this is like negative 12 centimeters here, and this is like out here is positive 19 centimeters or something like that. Okay. Yeah. And so and that's what happens. This restoring force of this kind, F equals f of x equals minus kx. That's a restoring force. And as I mentioned, there's other restoring forces. Um, so, but this is the one that is everywhere. And you guys in engineering, you're going to be seeing this out the wazoo. Electrical, mechanical, civil, chemical. Do they do chemical engineering here? No? Any kind of engineering, you're going to be, I mean, this is going to be right up there with F equals MA in terms of the size of your brain that is obsessed with these equations and stuff. All right, let's go to the next page and let's do a little more notes on oscillation, the spring force. Okay, so this is 227, 20, page 5. All right. F equals MA minus, which is like minus KX equals M X double dot. Now this is the compact notation. X with a double dot over the top of it. That's a compact notation for second derivative with respect to time. Okay, so this thing means d squared by dt squared times x of t. So now we've dealt with this before. Let's take our differential equation and let's convert it to m x double dot plus kx equals 0. All right, we just put the kx over on the other side. All right. Let's divide by m on both sides and we get x double dot plus k over m quotient times x equals 0. So now let's go and look at this. D squared by dt squared. I'll put this notation back. X of t plus k over m times x of t equals 0. So when you're looking at this now, you have to ask yourself, okay, I want a function that I could differentiate 2 times and have the same function back with maybe some constants out in front. Now we've already done this. It's sines and cosines. All right, so this one is sines and cosines, or I'll just write down sinusoidal with time. Okay, and so so the general solution for this is x of t is equal to some constant a times the cosine of omega t plus some constant b times the sine of omega t. So in general, you don't know whether you should use sines or cosines. Depends on the initial conditions that you're starting with. So initial conditions could be So initial conditions tell you, whether you should use sine or cosine or a mixture. So for instance, pull out to the right, then let go. Your initial condition is x of 0 equals maximum x, and v of 0 is equal to 0. All right? So you pull it out to some maximum extension, then you let it go, and then you start the clock. All right? Another initial condition would be give it a kick at the origin, at origin from rest. All right. So this one, x of 0 equals 0, and v of 0. No, v of 0 is going to be your kick. So like, positive or negative, it doesn't matter. Positive, you kick it to the right. Negative if you go to the left. All right. So those are two different initial conditions. All right. Now let's take a look. Let's differentiate this baby. All right. X prime of t, or x dot of t, is equal to, all right, cosine is a minus sign. The derivative of that is a minus sign. All right. So I always have to think it over. Minus omega times a sine of omega t. And then sine is positive. So this is omega b times cosine of omega t. And can you see that another differentiation is going to get us back to cosine omega t and sine omega t? All right, so we're doing good here. All right. X double dot is equal to, okay, minus omega squared times a cosine of omega t. Now this one brings out the minus sign in the second derivative. Okay, so you bring out a minus sign here the first time, and you bring it out over here in the second derivative. And now what you've got is minus omega squared times your original x of t. All right. So let's put that back into the differential equation. All right. So let's go back to the differential equation. All right. And so m, actually, let's put it in here. Let's put it in this one. This is the best. All right. So x double dot is minus omega squared times x of t. All right. So there's our substitution. We calculated x double dot. There it is. Now we also have plus k over m times x of t equals 0. All right. Now, if you factor out x of t, you get this equation. So what that means is that minus omega squared plus k over m is equal to 0. And my wonderful students, that tells you that omega squared, k over m is equal to omega squared. So your angular frequency in this is called the simple harmonic oscillator. This is called the simple harmonic oscillator equation. Okay. Anytime you see something like that, bing, oscillation, all right, automatically. And you engineers and physics and chem majors, biology majors, if any, probably not, but the rest of you, you're going to see it out the wazoo. You're going to see it everywhere. And that's a key, anytime you're working with some weird force and you can massage it into it looks like x double dot plus a constant times x equals 0, then you automatically, whatever the x is, whatever that variable is, it's going to oscillate. And that's something that's important. Okay, so this is so this means that the angular frequency is equal to the square root of that. Okay, now let's take a look at the units there. K, we didn't do this above here, but let's do it now. K times x, the units of K times x are newtons. And that's the same as kilogram meter per second squared. So that means that K is equal to newtons per meter, and that's the same as kilogram per second squared. So this is weird. There's nothing, I mean, it's a spring constant, newtons per meter, and but you can, so kilogram per second squared, that's like mass per square second. Newtons per meter. That's actually fairly intuitive. How many? So here's the question. It's equivalent to how many newtons does it take to stretch or compress a spring by 1 meter? Okay, and the answer to that is K. All right, K tells you how long you have to stretch it to get a full meter of pullback force. All right, so you push it to the right, the pullback force is to the left. So it's, you're pushing it out to the right, and the spring is pulling back on you. Right, so how far do you have to pull it out to the right to get a negative 1 Newton, or to get how many newtons does it take to pull it out to 1 meter? I'll put it that way. All right, so that's what the spring constant is. So this is kind of like stiffness. Yeah, it's depending on what material you use, how big the diameter of the coil is, how long it is, and also, is it a compression spring or is it a torsion spring? Those are a little different. Some springs, you twist them and they come back. They have a restoring force to twist them back to the original. Those are called torsion springs. But a compression spring is going to be linear, left and right, pull back and push back. All right. All right. Next slide, please. (227, 20, page 6). All right, so that's oscillation, and we've kind of dealt with the basics of an oscillator equation. Now let's do some advanced work. All right. As I mentioned before, the change of kinetic energy is equal to whatever force is parallel to the trajectory Hey, do you guys, show a show of hands, please. Do you know what the for two vectors A and B, do you know what this quantity means? A dot B, the dot product. Raise your hand if you know that. Boy, not everybody does. Okay. There's another one, another vector product, A cross B. Not everybody knows that, I'm sure. Uh, we're going to need both of those. Let me give you a little bit of instruction on those. It's pretty basic. If you have two vectors, I'll make them different length. Go ahead and make, so here's vector B, here's vector A. So different length, different angle. Here's theta, right in here. This one's called the dot product, or the scalar product, because it gives you a scalar. And it's basically this way: A dotted into B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And it's a scalar, right? So it's magnitudes and a cosine of theta, all right? So one way that you can think of this is the projection of A onto the B axis, all right? So this distance here is A cosine theta, all right? And so you can think of it as a projection, all right? Now this one up here, this is called the cross product or the vector product. This one up here, we're going to need that when we get to angular momentum. So I'll wait until then for that baby. Let me circle that in red. We're not going to need that today. All right, now let's draw, before we do the definition of kinetic energy and work, let's just draw a generic path. All right, just draw a curved path. And on the curved path, go to one of the curved parts and put a little increment of the path. All right, now this is going to be path sigma, capital Greek sigma. And the coordinate along the line is going to be S. So this would be like S equals 0 down here, and this would be like S equals 5 up here, for instance. So the parameter of this curve is S. And this little thing here is a vector for, let me just put a little arrow here. Okay, it's going to be infinitesimally small. That is a little increment of the S parameter, the S path, nicknamed capital sigma for capital S. All right, so that's ds, a small increment of the path. Path sigma, and it's equal to a unit vector, which if you knew the equation of the path, you could figure it out. So I'll put unit vector here with a little hat symbol over it, times a small increment of ds. Okay. All right. So we're going to do some calculus here. We're going to do some integration here, right? Because the change in let me write this equation again. The change in the kinetic energy is equal to a small increment of the force dotted into ds. All right. Now, that's for a generic path. For the oscillator, an increment of the kinetic energy is equal to, all right, the force is minus kx times I hat. All right. That's just the spring force law. And then we're going to dot that into, now, on the x-axis, we don't have a generic unit vector like we do here. All right, so this is generic for some generic axis S. On the x-axis, the increment, I'll write it this way, dx, and I'll make this a vector x, lowercase x. All right. Now that increment of the x-axis is equal to, let's put it all together here, minus kx times I hat times, or dotted into the quantity dx, a scalar, times I hat. All right. And so that is, let me draw that down here. So here's your x-axis again. And so here's a dx. There's your dx vector. And that's equal to just a little bit of a dx times I hat. All right. And so this is, you don't have any, I haven't put the equilibrium point on here, but wherever the equilibrium point is, well, let's put it down here. Let's put x equals 0 here. All right. So that means if you're out here, so go ahead and put a dot up here above the line. Okay. If you're out there, your force is going to be, of some magnitude. So this is your oscillator force, which is going to be equal to minus kx times I hat. Right? Now, the total change in the kinetic energy is an integral from start to finish. And that's equal to the integral. And we're going to add up all these little f delta s's here. All right. So that means you take an integral from the start to the finish of your path, f dot ds. It's the generic form for the harmonic oscillator. It's equal to x subscript I, x subscript f, minus kx times dx times I hat dot I hat. What's I hat times I hat? Dotted into I hat. What are the I hats known as? Do they have the dimension? Do they have units? No, they don't. They're dimensionless. I dot I they're the same direction, right? So the cosine of theta is 0. What's the cosine of theta? Or what's the cosine of 0? 1. So this is just equal to 1. Okay. So you're changing the kinetic energy. This is known as the work from the start to the finish of your increments of kinetic. So every inch of the way, you're getting a little bit different I'll put a minus sign out here, minus kx dx. Oh my goodness. That's an almost impossible integral to do. Have you ever noticed that? You think? What's the antiderivative of that integral or of that integrand? Integral of minus kx dx is equal to what? Negative kx squared over 2. All right. Not minus 1/2 kx squared evaluated between xi and xf. All right. And notice there's a minus sign in there. All right. So you could, depending on what xi and xf are, you could lose ke or gain ke. All right. Next page, please. So let's work out some of this thing on the next page. All right. So what was that? 5, 6. Boy, we're doing a lot of pages. I'm running out of paper, graph paper. I'm gonna have to get a new notebook. So this is page 7 to 27, 20. So the work, which is the total change, I'll call it delta ke. That's going to be equal to minus 1/2 k x squared evaluated between xi and xf. All right. Now let's draw. So that's the formula from the previous page. So that's the work formula. So don't for the harmonic oscillator equation. Okay. Now don't mistake that or mix it up with the weight force. So that uses a capital W usually too. So just from the context, you should be able to tell. So read carefully and listen carefully. All right, let's set up an axis. And let's make it a tabletop. And here's my wall and my springs attached like this. And let's put x equals 0 here, the equilibrium point. And let's pull it all the way past equilibrium a little bit further here, out to here. And we'll call this x max. Okay? So here's my weight, my mass m. Spring is typified by the spring constant. All right, now, let's say that my initial conditions are x of 0, or xi, equal to x max. Okay, so we're pulling it out that far. And v of 0 is equal to 0, 0.0 meters per second. Okay, so there's no kinetic energy. And the reason for that, if you forgot, the kinetic energy formula is 1/2 mv squared. Okay, and that looks an awful lot like the what do you call it? The 1/2 kx squared that we got here. See that? And notice that there's a factor of m and k between these two. And my wonderful students, that is not a coincidence. All right. Now let's take a look at this. All right, let's go down here and do the work expression again. Minus 1/2 k x squared evaluated. All right, now let's put in the numbers. Starting point is x max. Final point is equilibrium 0. So let's just do the right-hand side of the motion on the way in. All right, we start out there at x maximum, and then we let her rip. All right, the first thing that's going to happen is it's going to come back this far. All right, and then the interesting thing is it's going to compress. It's going to go past there and compress. But let's just do the work done by the spring in from starting point to final point equilibrium. All right, so here we go. All right, so how do we do this? Minus 1/2 k. So this is, now how does it go? Is it x max squared minus 0 squared? It's 0 squared. Are you sure? You do the top one first? All right, good. 0 squared minus x max quantity squared. All right, now x max, might be, it might be, like 0.12 meters or something like that. All right, so this is going to be a positive number. We're subtracting it from 0. So this stuff in here is negative, negatory. But we also have this minus 1 out here, or this minus sign out here. So this is going to be equal to positive 1/2 k times x max quantity squared. And that is the work done. That is the change in the kinetic energy from max extension to equilibrium. All right. Now, let's think about, let me draw in a ghost of the block over here, red. All right. So go out to minus x max, negative x max. So like negative 0.12 meters or whatever you choose. And let's think about the change in the kinetic energy. So let's do a new problem. Minus 1/2 kx squared. And let's start at equilibrium. All right. And we'll go out to minus x max. And so that's going to be equal to minus 1/2 k. All right. So then I go minus x max quantity squared, right? Uh-oh. What's minus x max quantity squared? X max squared. The minus sign cancels. Uh-oh. Minus 1/2 k times x max quantity squared, which is opposite to the previous result. All right. Now that's important. So let's think about what we got here. We have 0 kinetic energy here. All right. And by the time we get, now this is up here in the first half of the trip. By the time we get to equilibrium, we got a ton. I mean, this is how much we got right here, 1/2 k x max squared. Right, so we got, so depending on k and, x max, but it's going to be a positive number. And you gain that on the way to equilibrium. So from max extension, which is 0 kinetic, to equilibrium. So what that means is at equilibrium, max KE. And for us, for this example, 0 KE at X max. All right. Now, let me ask you a question. From 0 out to negative X max, we lose the same amount. So that means out here, you've got zip zap, Cecilia. We got zero kinetic energy out here. What? And that, my wonderful students, is a result of the restoring force. It's an oscillation that trades position for kinetic energy. All right? So it looks like the kinetic energy is not a constant. It just varies, depending on your initial conditions, which we had up here. We know that it's zero out here, it's maximum at equilibrium. And now, if you start it with a kick right here, it's going to be a little different. But you're still going to have maximum kinetic here, all right, as soon as you kick it, all right? So the energy oscillates as well. I should say the kinetic energy. All right, it changes from max to zero back to max. Now, the potential energy is the opposite of the work integral. Okay, so SPE, spring potential energy, is the opposite of the work integral. All right, so that means whatever we had for the work integral, F delta S or FDS, we put a minus sign in front of it. So a minus sign in front of initial to final of F dx. So we already know what that is, F dx. That gives us a minus sign. So this is equal to the minus of minus 1/2 K x squared. All right. Evaluated between initial, and so this would be the delta, the change of the spring potential energy between initial. Now what that means is that the change of the kinetic energy is opposite of the change of the spring potential energy. And so what that means is that 1/2 kx squared, which is the spring potential, so this is 1/2 in general, 1/2 kx squared, plus the 1/2 mv squared, that's equal to a constant. Because what happens is, this is Ke, this is spring potential energy. Whatever the kinetic energy loses goes into the potential. And if you think about it here, the change in the SPE from 0 out to negative x max is going to be positive. You're gaining potential energy as you lose kinetic. All right, so out here, you have max SPE. And same thing out here. At x max, you have max SPE. All right? And this constant is known as the total mechanical energy, E. All right? And that is a constant of the motion. We call it a conserved quantity. All right? So this is the most simple form of what we call the conservation of total mechanical energy. Now, you engineers and physicists and chemists in training, you're going to need to know this all over the place. conservation of total mechanical energy. And you know why? Because think of all the different forces in the universe. I mean, this one is related to the spring force. But how about the force of downward gravity here on the surface of the Earth? That's minus mg, or that's mg. Think about the gravitational force, which we haven't studied yet. We're going to study it. That's what we call an inverse R squared force. That varies significantly with distance away from the center of the Earth, or the center of the sun, or the center, center of the galaxy, or whatever you're thinking about. The electromagnetic interaction, the Coulomb force between protons and electrons, also varies with R squared, the distance between the electron and the proton, or between a bunch of electrons and a bunch of protons, like a nucleus and a bunch of electrons, or between a okay, raise your hand if you've had a chemistry class in here, like intro. Okay, it's a bunch of you. And what do you get in what kind of bond is it for sodium, for NaCl? It's ionic. So the sodium gets ripped off. It loses an electron, becomes a positive ion. All right. So it's got a lot of protons and stuff in there, but it's got one extra proton that it has electrons after it gets stolen. The chlorine steals it. The chlorine is one of the big thieves. Alibaba and the 40 thieves over there on the seventh column of the periodic table. So that becomes a negative ion. So the force between them, that is and you know what? You can get oscillations there when you do all the physics for that force law. So we've done this is probably about the easiest one, F equals minus kx, but it leads to this. Now here's another thing. Whenever you see, here's another thing to look at. This is the same as 1/2 kx squared plus 1/2 mx dot squared. So whenever you see a potential energy that's the square of a coordinate, I mean, you're always going to have, x dot, the time derivative of your coordinate is always going to give you kinetic. But if you have a potential energy that's the square of that same coordinate, you always oscillate. This is an oscillator condition. And in quantum field theory, when you're trying to figure out, black hole tunneling, from out of a quantum field into a lower state, you see that. You say that, but it's not a coordinate like a position coordinate. It's a quantum field that is squared and proportional to the derivative, the square of the derivative of the field. So you see it all over the place in quantum mechanics, quantum field theory, as well as regular mechanics, which is what we're doing here. All right, let's take a little 10-minute break. Go ahead and use the men's room and the ladies' room if you want. I want to think some. You can talk if you want, or go get a snack. Let me pause this. Can you bring that down? Let's take, as I mentioned, the equations of motion and stuff are from chapter 2, from chapter 15.1 and a little bit deeper into chapter 15. Let's take a look at some of these images. Here's the basic oscillation, and this one, the vertical The vertical axis is x of t. So this is kind of a weird way to draw it, but it's a sine curve. No, this is a cosine curve. And the period, capital T, is the amount of time it takes to one full oscillation. So bump to bump. So this would be like, you know what this is like? It's like pulling it out to maximum extension at plus A and then letting it go. And right here is where the position is 0, right? So that's a quarter of the cycle. Here it is over here. This is position minus A. So this is max compression. So go ahead and make a sketch of this if you want, and make a note that this is, minus A. That's negative X max in the notation I was using. So that'd be like negative max compression, and that's half a cycle. That's half a period through. Now, 3/4 of the way through the cycle, you're back here at 0. You're back at equilibrium. And then 1 full cycle, you're back to your starting point up here. Now, I want to ask you an iClicker question. And this one, now make sure you label that the vertical axis is x of t, and the horizontal axis is time. I'm going to ask you go ahead and hit the refresh key on your calculator or your clicker. Hit the refresh key. Now, riddle me this. Riddle me this. The derivative of this function, d by dt of this function, how do you physically interpret that? The derivative. I mean, in terms of the graph, to calculate the derivative, what does that mean in terms of this graph? Remember? Huh? That's physically what it means, but on this, it does mean the velocity. That's correct. But what does it mean in terms of this graph? All right. Let me make that the question. What is the geometric, and I'll give everybody correct answers on this, the geometric interpretation of the derivative on this graph? What does it mean in terms of this graph? And type in a word or phrase, and then hit the send key. Actually, this is correct. Listen to all that clicking. Nice. The sound of thought. Angel, what you doing there? What you doing there? Just looking at my stuff or at the textbook? What are you typing in?
It's like a goal statement for like this workshop after.
Oh, okay. You're not paying attention to lecture?
I sort of am.
Boy, oh boy. Okay, 30 seconds to type in your word. or phrase. 20 seconds. Hurry up. Ten seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Close that. All right, let's take a look at your answers. Yeah, this is something I didn't think of. Negative sine. Yeah, that's the derivative. Sine of t. Sine is L tan. Well, I said I would give everybody points, so I'll give that one. I don't know what. Oh, minus plus minus. That's interesting. I think that's correct. They're thinking about dips and bumps. Sine of t. Isn't there a parenthesis symbol in there? No? Okay. Everybody's thinking sines here, but you know what I'm thinking? Sine, average. Average AVR, I guess that means average. I don't think that's correct. Decreasing negative. Decrease negative. Inverse. That's not correct, but I did ask for L tan is negative sine. I don't know what that is. Max plus min. I'll give all these oscillation shift FL3. I don't know what that is. Shift flip, shift phase, sine, sine, sine. There it is. Slope. That's what I was thinking of. Tangent. That's also good. All right. Now, I'll give everybody correct points on that. Let's look at this. Up here, up here at plus a times t equals 0, you're starting at maximum, but what is the tangent up there? 0, it's flat. So that means your velocity is 0 up there. Now, where is it the steepest? Right here. So max velocity, no, I should say max speed at equilibrium. All right. Now, down here, we're all the way at max compression. And again, the tangent, the derivative is zip zap. So zip zap speed. We don't have any. Got plenty of distance, but no speed. And we're back to max steepness here. And it just oscillates back and forth. Now, let's take a look at this one. Look at this picture. This is 15.5. I've never seen one like this. But this gives you 1 1/4 cycles for this oscillator. All right. And so it kind of traces it. So this is what it would look like if time were on the vertical axis and x were on the horizontal axis. Right. So here's max extension over here at positive A. Is that what they have down there? Yeah. This is positive A out here, max extension. And make a note, that's also where the leftward force is the strongest. All right, now look here. This red arrow, it's still good, but it's not as big because x is smaller here at this intermediate point. You know, this is the max x. So wherever the extension or compression is maximum, you have maximum net force. Now here's max compression over here at minus A. Actually, let me go to this next slide. All right, here, this is a little bit better. Here's positive A. Here's minus A over here. And you can see that the red arrow here to the right is longest and it's rightward. But right here at equilibrium, that's x equals 0, you don't get jack for force, but only for that instant that it passes the equilibrium point. Because as soon as you get to the left of it, you're starting to get some rightward newtons. Okay, slowing you down. So this is slowing down, and out here it gets to maximum compression, And then now you're moving right and your force is to the right, so you're gaining speed until you get back to equilibrium. So let's look at that. All right. So here's equilibrium. You pass, no, equilibrium's up here. I cut this off a little bit too. Let's go back up here. All right. So here's equilibrium. No, that's good. Yeah, this is good. This is equilibrium right here. Okay. So there's equilibrium, no force, maximum kinetic energy, maximum speed. Now, you can't really say max velocity because the velocities are vectors. All right. You could say max leftward velocity or max rightward. Down here, this would be max rightward velocity. All right. Because from max compression all the way back to the equilibrium, you have rightward force in the direction of your motion. So F dot dx is a positive number, whatever it is. So make a note of that. From max compression back to equilibrium, F dot dx is positive. Every increment of kinetic energy you gain is positive. But over here, from equilibrium all the way to the left, your motion, Andres, is to the left, but your force is to the right. So F dot dx is going to be negatory. That means you've lost a little bit of kinetic energy per inch. All right? Because the force and the motion are in opposite directions. All right? So here's the equilibrium, and then of course down here is the other equilibrium. Question, Angel.
The two, one's 1/4 and the other is 3/4.
That's right. This is the full cycle. So the period T, remember we've cut off a little bit of this. So let's go back up to the top here. Okay, so here's the full, so time T equals 0. Quarter of the way you're through the cycle, you're at equilibrium. All right, so this motion from max extension to equilibrium is quarter of a cycle. Now, from equilibrium out to max compression, another quarter, total of 1/2 period. Back to equilibrium here, another quarter, total 3/4.
So it's bringing back.
Mm-hmm.
You started it from extension.
Right. I started at v equals 0 at x equals positive a. All right. And it goes another 1/2 of a cycle down to here. So you're back to max compression down here. All right. Now, can you imagine for quiz 2 how difficult I could make multiple choice questions based on this diagram? Because look at all the different things you have to think of. Force, direction of force, size of force, velocity, size of the velocity, the speed, direction of the velocity, position, left or right, max or 0. Is it max left or is it max right? Or is it the equilibrium or is it somewhere in between? Right? So and I teach my students in Physical Science 1121 about this stuff. And I give them some tough multiple choice questions. So I'm not kidding about that on quiz 2. You're probably going to see something tie your brain in knots. All right, so here's the 2 equilibrium positions. Now, I want to go over for the last half hour, 40 minutes or so, a little workout with potential energy and kinetic energy and how that varies with position. I guess that's basically the definition of potential energy. So let's go back to the doc cam and work out some stuff here. Okay, the spring potential energy, instead of calling it SPE, I'm just going to call it U of X. All right, that's equal to 1/2 kx squared. And in actuality, it's defined at any point on the x-axis. So potential energy in general is known as the energy of position. Kinetic energy is the energy of motion, and they're complementary functions. Let's take the first derivative, du by dx. That's fine. We got a function of x. Let's take its derivative. What's the derivative of that baby? Kx. And that's almost the same as the spring law force. All right, Tanis? So this means that for the harmonic oscillator function, the force is equal to the opposite of du by dx. This is also known as the gradient. In 3 dimensions, you would call this the gradient. But for something simple like harmonic oscillator, motional on the x-axis, it's just one derivative instead of 3 spatial derivatives. But this is always the case. This is the relationship between force and potential energy. So the force, if you have a potential energy function, the force is the opposite of the spatial derivative. Of the potential energy function. Now, some of you guys are going to get into 2049, and you're going to be working in 3 dimensions in 2049. So you'll be doing more of these gradients. This is about the simplest one that you can do because it's only 1-dimensional. There's 2-dimensional spatial oscillators that you can set up, but this is an important result. It's very, it has conditions. So I'll put an asterisk next to this. Under certain conditions that we'll work on next week relating to friction and stuff. Conservation of energy. So, but the interesting thing for the spring is it's defined at any point. This function is defined at any point. So you can always figure out delta U from point A to point B, and therefore you can always figure out kinetic energy gained or lost from point A to point B. All right, so let's do a little problem here for the next few minutes. Let's do an oscillator problem with K equal to 500 newtons per meter. Okay, so that means you have to pull with 500 newtons to stretch the spring a full meter. So this is kind of a soft spring. And you know, if you go on the internet and you go and try to buy springs at a spring manufacturer, you know, like Acme Springs or whatever, they'll list the spring constant. They'll list the mass of the spring, the length, diameter, spring constant, all that stuff. All right, so let's do this, and let's say that the mass of my object is equal to 2.4 kilograms. All right. So let's study the motion along the x-axis. Let's put x equals 0 here for the equilibrium, and let's go out to x of 0 equal to 0.16 meter. All right, I'm just making up some numbers. We'll do some calculations here. All right, and let's say that we pull it out and hold it. All right, so kinetic energy here is 0. Potential energy, U is equal to maximum. Let's figure that out. Okay, so at x of 0, U of x of 0 is equal to 1/2 times 500 Newton per meter times 0.16 meters quantity squared. Right, so there's your calculation. 0.16, that's 0.0256, correct? 0.16 squared? Yeah, 0.0256. So this is equal to 250 Newton per meter times 0.0256 square meters. Okay, now look at those units. Okay, we can cancel a meter here, and we can cancel one of the meters in the numerator. So, all right, what's 250 times 0.0256? So it's about 5 or 6 something? 6.4? Okay. So U of x of 0 equals 6.4 Newton meters. All right, and that's equal to joules. 6.4 joules. And that's also equal to 6.4 kilogram meter squared per second squared. All right. So all three of those are handy for working on, problems. So let's do, now this is maximum extension. So let's make a note here, max extension. All right. And so I'm going to go 4 blocks to the left and map out minus x of 0. This is max compression. So my dude, not there, right here. All right, so this is minus x of 0. All right. So let me ask you a question. What is the potential energy at minus x of 0? In other words, max compression. Same, 6.4. Good. Okay. Same as at max extension. All right. Now, where is U equal to 0? Mm-hmm. So what it looks like here is we have a high value for U over here on the right, similar high value over here on the left, and zip zap. Does it ever get below 0? Does U ever get below 0? No, it can't, because unless we're in an imaginary x coordinate, which we don't normally use that even in quantum mechanics. So U is always positive in this case. Matter of fact, what kind of a function is that? What kind of a shape is that? It's a parabola. Yeah. And it's an upright parabola. All right. So let's make a sketch of that. See if I have some room here. All right. All right. Let me go down here. All right. All right. So the function, I'll draw it in red, is 0 right here. And let's go up 6.4 blocks. All right, so that's about 6.4. And this one's about 6.4. So right about there. And now you could draw on a graceful parabola. And actually just keep it going. Put a little arrowhead out here to symbolize that it keeps going. So this is u of x. All right. The min, the global minimum, is x equals 0. There is no global maximum. Now, so what that means is theoretically this function is defined for all x. Now, physically, your spring is going to pull apart or break. You know, once you get, you know, like it might break apart at 20 centimeters, 0.20 meters or something like that. Or it might bend at negative 20.0 or negative 0.20 meters. Okay. But theoretically, it's defined everywhere. Now, this the global minimum is important. Now, let's put up, I'm going to draw a dotted line in red between my two. Okay, so this is 6.4 joules. And hey, you guys, out here, the potential energy is 0, or is 6.4. What's the value of the kinetic energy out here? Right. So that means that the total energy is 6.4 joules. All right. And you can use that to figure out, for instance, the kinetic energy at any other point. So let's go halfway. No, let's go a fourth of the way in. So this is 0.04 meters, 4 centimeters, almost back to equilibrium. Let's work on that problem for the next few minutes. All right, let's figure out what V is equal to. Actually, why don't you guys take 10 minutes to figure out V at the speed, in other words. What direction is the velocity here? On the first time through, after we release. Velocity is negative. So let's just get the speed. All right. So figure out V at x equals 0.04 meters position. Given all this stuff. And we know the mass. Where was that? 2.4. Okay. So we can figure out the speed from this. All right. Go ahead and start. And that'll be a classwork problem. I'll do, and I want to get your answer in 10 minutes. Go ahead and circulate around, Tyler. And we'll click it in on the iClicker. And then we'll analyze.
Why is it negative? I didn't notice that.
After release, it's going to be positive on the way back, but right after release, it's moving to the left.
Oh, okay.
Right, and then it passes. But then after it hits max compression, it's going to come back to the right again, and so it's going to, yeah, it's going to have positive speed. So it's tricky to keep all the directions and everything
So like in a work
straight.
problem, you have to like.
I'd have to say right after on the first pass.
Okay.
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 But the speed, it ends up the speed doesn't matter. The velocity does, but the speed is defined at every point x as well.
Can you repeat the question?
Yeah. What is the speed at x equals 0.04 meters? Who's the potato on Instagram? Somebody named the potatoes on here. Are you the potato?
Maybe. So could I think of this as like an upside down baseball problem? Would that help me?
No, it's not. It used the conservation of kinetic energy formula.
Okay.
You know, equals 1/2 kx squared plus 1/2 mv squared. Unbelievable. Okay, students, when you get your answer for the speed, you know, something point something meters per second, type it in your iClicker and hit the send key. Let's go to the document camp. All right. So let's work this out. Watch how I do it. You know, maybe pick up something. It might be different from how you did it. Still be good. All right. So the key is out here. Once you know the both the kinetic and the potential energy, you can write down automatically that the total energy is equal to the sum of those two, which in this case is 6.4 joules. All right. Now, that is true at every other point, including 0.04 meters. All right. So I'm just going to, so we haven't figured out the speed yet, but we're gonna. Now, the thing is, this stuff here is equal to kinetic plus potential. Okay, so really what you've got is 6.4 joules equal to 1/2 mv squared plus, what was K, 500? Okay, so this is 250 newtons per meter times 0.04 meters quantity squared. So and we know what M is. M is, what was M? 2.4? Okay, so this is 1.2. So you can see that you can, so 1.2 kilogram times V squared plus, now what's this? Now I need a calculator. Let me use my phone. 250, so what is that, 10? No. 250 times, oh no, wait, it's 0.04 squared. Hold on a second. All right, so 0.04 squared here times 250, right, 0.04. So this is 0.04 joules right there. So that means that I've got 6.56 joules of kinetic energy here. Oh, you're right. 0.4 joules. Yeah, that's, I got it right in front of me. All right, so this is 6.00 joules. Oh, this works out pretty nice. You know, I just made this up. I didn't mean it to be easy, but it actually does turn out to be easy. So this is 5, and a joule divided by a kilogram is meters squared per second squared. So that's V squared. So V is equal to the square root of 5, which I know is 2.23 meters per second. All right. And let's take a look at your guys' clicking answers. Now this one I'm going to grade carefully. All right, here's your, uh-oh, that looks a little like too much round off. Okay, I'll be nice about it. This is the velocity. You can't? Oh, sorry. Okay, so 2.24 is a little bit too big. That's a velocity. What? 2.236? Okay, we'll get that. We'll accept that. So that's good up here to 2.24. This one I'll accept for today, but not on the test. I'll accept this one. 2.31, that's off. 0.54. I'll accept this one, but not this one. I'll accept this one as a velocity only because I'm being nice. It should be. It's a speed that I want, so it should. There shouldn't be any negative signs, but I'll have mercy on you for that. So, question.
Can you go back to the work?
Yeah. What do you want? You have a question?
No, I got it.
All right. Students, we're about to dismiss. We've had a long session today. Here's your reading homework. I want you to skim 5.6 about Hooke's Law, Chapter 15 about oscillation. Skim those two, and then start studying for depth in Chapter 7 and 8. And you'll already know a bunch of stuff in 7 and 8, especially after today. Okay, you're dismissed. I'll see you next week.